At the core of industrial automation is a massive mismatch in scale. On one end, you have digital logic operating at a microscopic level. On the other, heavy-duty machinery exerting hundreds of pounds of physical force. A programmable logic controller's central processing unit handles calculations using highly sensitive, low-voltage direct current, typically just 3.3 or 5 volts. That low-voltage processor lacks the electrical capacity to directly spin a three-phase industrial motor or fire a heavy pneumatic solenoid. If you connected them directly, the current draw would instantly destroy the CPU. The solution to this power gap lies in a specific class of hardware known as output devices. These act as the final control elements in an automation network. They take the low-power commands generated by the PLC and translate them into direct physical action, whether that is mechanical movement, fluid control, or triggering audible alarms. If the PLC's CPU functions as the brain of the operation, making the decisions, the output devices serve as the physical hands doing the heavy lifting on the factory floor. Understanding how a control system works requires tracing exactly how a delicate digital command safely crosses the electrical gap to become brute physical force. To see how that gap is bridged, we can track a single logical command step by step from its creation to its execution. This block diagram maps the signal's journey. Originating in the CPU, the processor executes logic and dispatches a low-voltage signal to an address like Q0.0. Its first destination is the output module. This module performs two critical functions. The first is electrical isolation. It creates a physical barrier that protects the sensitive CPU from high-voltage spikes or short circuits that routinely occur on the factory floor. And the second function is signal amplification. The module uses the microscopic logic signal from the CPU to trigger a switch on a separate, much larger power source, driving the field devices. To achieve this amplification, the module relies on specific internal switching mechanisms. Engineers select mechanical relays for versatile switching, solid-state transistors for high-speed DC applications, or triacs for alternating current loads. Only after passing through this firewall of isolation and amplification does the signal move to the third stage, the physical output device. Finally, the signal reaches the process stage, where the device's mechanical action directly manipulates the real-world system. The output module is an active barrier and amplifier that clearly divides the computer science of logic from the electrical engineering of the factory. Before a signal even leaves that module, the system architecture must account for the exact type of signal the specific field device requires to operate. Looking at this technical reference, we see the first major category, digital outputs. These are strict binary signals restricted to two states, a 1 for on or a 0 for off. This binary control is required for devices like motors, indicator lamps, or solenoid valves. The second category, analog outputs, provide a continuous, variable range of control, measured in standard ranges like 4 to 20 milliamps or 0 to 10 volts. This allows for precise, scaled control, necessary for adjusting drive speeds, managing PID loops, or throttling temperatures. A digital module cannot output a variable 4 to 20 milliamp curve, and an analog module cannot output a binary switch. The automation engineer must physically install the exact module type in the PLC rack that matches the load's requirements. The physical reality of the required work, whether demanding a blunt on and off switch or precise continuous throttling, strictly dictates the electrical architecture of that output channel. Translating this theory into practical application requires the ability to read the system's wiring schematic, mapping logic to physical circuits. This standard schematic illustrates output wiring for a 24-volt DC system, bridging internal logic to hardware. The top horizontal line represents the plus 24-volt DC bus, supplying external, high-power energy required for the field devices. Starting at logical address Q0.0, we see the internal transistor acting as a switch. When commanded on, power routes directly down the wire to its physical load, a contactor coil labeled K1, starting a heavy motor. Moving to adjacent addresses, Q0.1 routes power to illuminate a lamp, and Q0.2 traces down to a solenoid valve. Finally, the circuit completes at the bottom, linking all devices to a common 0-volt DC return path. When a programmer types a software tag like Q0.1 into their logic code, they are creating a direct, hardwired instruction for a physical transistor to complete a physical circuit on the factory floor. Returning to this technical overview, we see the wide variety of devices these circuits power. Regardless of whether they convert electrical energy into mechanical rotation, fluid dynamics, or simple alarms, every one relies on the exact same architecture of electrical isolation and amplification. For an engineer, reliable operation hinges entirely on correct output selection. The module's switching capabilities must perfectly match the physical demands of the field device. This brings us to the definitive definition of the entire concept. Output devices are field devices which receive signals from the PLC and perform the required action to control the process or machine. Without output devices, a PLC is a calculator isolated in a metal box. This physical output architecture gives the logic its real-world power.